Hi, this is Pat Kaplo, and I am solving problem number 8 on page 162. It reads, a 330 kilogram piano slides 3.6 meters down a 28-degree incline. It's kept from accelerating, those are critical words there, by a man who is pushing back parallel to the incline. There's a figure there. The effective coefficient of kinetic friction is 0.4. Calculate A, the force exerted by the man. So I've drawn a quick free body diagram here. You can see that I've gone ahead in green and rotated the coordinate axis system. And in this case, now I need to draw my vectors in. We know that there's a weight vector in the downward direction here, and I've drawn it in a dashed line because ultimately we need to resolve that vector into the x and y components for it to be useful to us. So we have therefore an x component of that weight, and we also have a y component of the weight. There's also a normal force that's normal to the surface, or 90 degrees to the surface of the incline, that is directed upward. It's going to be opposite the y component of the weight. There's since it's sliding down the incline, it's important to remember here that the direction of motion is down the incline. So therefore, the frictional force is acting opposite the direction of motion, or up the incline. So this whole thing is kept from accelerating down the incline. If we look at this sketch here, we can see that the x component of weight is larger than the frictional force. So the whole thing is kept from sliding down the incline by this additional applied force, which we can call F sub APP for the applied force. So there are three forces in the x-plane, and that's going to allow us to set up our dynamics equations here. So let's take a look at this. We'll start in the horizontal plane. And as usual, it's a good idea to ask yourself the question, either internally or at least here formally on paper: is the sum of the forces in the x direction equal to 0? And the answer to this question, of course, is yes, because as the question states, the piano is kept from accelerating. It slides down the incline at a constant velocity. So if I use the conventions of the x direction here being positive, and this is the negative x direction, I can say that the x component of the weight minus the frictional force, since it's in the negative direction of my tilted coordinate axis system, minus the applied force is equal to 0. That's my equation for the horizontal direction. In the vertical direction, I can say the same thing about the sum of the forces in the y direction. They are equal to 0. Yes, they are. So in the vertical plane, I can now say that the normal force, which is in the positive direction, minus the y component of the weight is equal to 0, and that the normal force is equal to the y component of the weight. We can use some of our vector resolution. Keep in mind that we do know that this angle theta here on the incline is also equal to the angle that the weight vector makes with the y-axis. Now, since we're referencing the y-axis, we have to flip our conventions for our trig conventions for resolving this vector. So we can now say that the normal force is equal to mg. Now, in the y direction, it would normally be the sine function, but we're going to use the cosine function because we've referenced the y-axis, mg cosine theta. In the horizontal plane, I can further work with this by basically calling the x component of the weight mg times the sine of the angle theta, 28 degrees, minus the frictional force, which is, of course, mu times the normal force, minus the applied force, which is ultimately what we're trying to solve in this problem. It makes sense at this point, then, to take this term and move it over to the other side because we're trying to isolate it. And also, we're going to ultimately substitute this expression for the normal force in back to our horizontal plane. So now I'm going to get mg sine theta minus mu times mg cosine theta is equal to our applied force. At this point, we're ready to kind of substitute some of our initial conditions. Let's go ahead and write that up on the board. We know that the mass here is 330 kilograms. That's given to us in the problem. We know that the angle theta is 28 degrees. We also, although we don't need it just yet, the displacement or the distance in the x direction is going to be equal to 3.6 meters. That'll come into play a little bit later when we're calculating our work. And the effective coefficient of kinetic friction, or mu sub k, is equal to 0.40. Now I'm ready to do some substitution, so I can say that the mass, 330 kilograms, times 9.8 meters per second squared, times the sine of 28 degrees. Now I'm going to have to subtract all of that from mu, which is my coefficient of friction, 0.40, times m, 330 kilograms, times g, which is 9.8 meters per second squared, times the cosine of 28 degrees, cosine 28. All of that's going to be equal to my applied force. Now, when I run that through my calculator, I'm going to get 376 newtons. That's what I get. You have to keep in mind order of operations here. It's easy to kind of get this mixed up in your calculator, but 376 newtons will be equal to the applied force. And then once we deal with our significance, we can go ahead and round that to 380 newtons. Would be the force required by this guy to keep the piano from accelerating down the incline. 380 newtons up the incline. This, of course, is problem number 8, part A. If we move on,